Okay, so let's start. So this week we'll do two exercises. One of them will be about freeness, and the other one that we'll do soon will be about the Cauchy transform. And they are both going to be rather easy. The main goal is to make sure that we all understand the definitions that we've seen in class. I will say that the exercise we'll do about freeness is the most important exercise about freeness. It's really easy. And I will I'll try to explain why is it so important. So the exercise goes as follows. So we start as usual with a non-commutative probability space. Non-commutative space. And we have B, a subset of A. I'm not doing the fancy A now, it's just A, there will be no other A's. So B is a subset of A, and it is a unital subalgebra. Meaning that it is a subalgebra and it contains the unit of A. And also, so we have B and we have an element U in A, which is a Haar unitary. And we try to summon our knowledge about of all the things that we've learned about Haar unitaries and non-commutative probability spaces so far in the course. And now, and we also know one more fact, and we'll recall soon what it means. We also know that B and the set U and U star are free. Now, by saying this, recall the definition we've seen in class today about freeness. So I need the definition about, I can define it on subalgebras. I can also define it on sets. Here I have a kind of a mix. This is a subalgebra, this is a set. So by this, I mean that B is free from the algebra generated by those two elements. And what I need to prove is that B is also free from the set I denote as U star BU, okay, which is an algebra, which can be verified, but I'm not going to do it. I mean, it's closed under addition and multiplication, and its definition is just all the elements of the form U star BU, where B is in B.
It's closed under multiplication because U is unitary, right?
Yes, it is closed under, exactly. So if I have, so addition is clear, but because, I mean, from the algebra definitions, but if I have star B1 U times star B2 U, then this cancel out, and this will be the prime. Okay, so this is an algebra, and what I need to prove about it is that B is now free from U star BU. Okay, given that B is free from the Haar unitary. I started. Exactly. That's the, but let's, about what's the meaning of this notion, that's why it's the most important exercise. But before I dive into the meaning of all this, what I want to discuss is how do we prove such a statement, and our main goal is to recall the definitions, because we're going to use them now for a while, until the end of the semester. Okay, so what does it mean that B and the set U and U star are free? It means that whenever I have elements, say B1, B, and elements, elements of the form, the elements that are formed by these, so powers, yes, powers of the Haar unitaries. Not only powers, it can be also polynomials and include the constant term also. So because it's the algebra generated by those and by the identity. So let's call them I don't know, V1 up to Vk in the algebra generated by U star and the identity. We don't need U star. Right. Yeah. So such that all of them are centered according to phi. So phi of Pi equals phi of Ej equals 0 for all of them. If I have such a sequence, then that's just the definition of freeness. Phi of the product V1, V1 to V, Vk equals 0. That's the definition. Now, what I want to show now is that B is free from this set. So now instead, what I want to show is that if I put some elements here such that these are in the set U star VU, then this still holds. So this is my goal, right? To show this part here. That this is going, phi of the product is going to be 0. But we're not there yet. Okay? This is our goal. Now, the way we do it is by first looking at the elements of this set. So let's look at one element here. Let's call it V. And we know that V is in U star VU, which means that it equals U star, let's call it CU for some C in V. Okay, that's by definition of this algebra. And we also know from here, from the condition on the left-hand side, that phi of V equals 0, right? That's the case we care about. And so we know that phi of U star CU equals 0. But we know, recall, that B and U are free. And for such products, we know how to calculate them for free elements. We've seen it in the lecture today. And this also equals, from this side, this also equals phi of U star U times phi of C. And this equality holds because these are free. E and U are free. And we saw the program. Okay. And U star U is just the identity. So this, and this tells us that the case in which an element in the algebra U star BU is centered, it means that the element that it was generated from is centered itself. So now what I want to show that the product of these is 0. So instead of writing it down first explicitly as the, let's write it down. So what does this tell us? So if I look at phi of v1, v1, v2, v2, up to vk, vk, this equals, for some values c1 to ck, equals phi of v1 u star c1 u, then v2, then u star c2 u, right? I replaced every v with the u star cu, and so on up to vk u star ck. This equals this for c1 up to ck in B such that they are centered. Right from the observation we had here. And now I have a sequence of 2k elements from the original algebras B and U star, and they are all centered. And why are they all centered? The B's are centered by our observation, by the requirement here. The C's are centered by the observation we had before, and the U's are centered because it's a Haar unit. Okay? And we know that Haar unitaries, we know much more about them, but in particular, phi of U equals phi of U star equals. It's also true for every positive power. So here, by definition of freeness, this equals 0. Sorry. 0. So by freeness, all this equals 0. Okay. So before I say anything about the meaning of all this, questions about the technicalities.
Assuming that an element is Haar unitary is quite a strong assumption. We only use the unit that U was unitary and centered.
Um,
We need to take like P unitary, P Haar unitary. Like you don't.
Yeah, that's a good point. Let me think about it, whether I assumed anything else here. Good point. It feels to me that I need the Haar unitarity for something here, but yeah, I don't quite see it here. I mean, now that I think of it for this proof, I don't need anything more. I probably could have extended the definition of this set to have powers of the unitaries here, and it will maybe it won't hold because it won't be an algebra. So I need to rethink it. But
This is an algebra for any unitary. u, right?
Yes, but if I extend it to powers of u, then I'm not sure. I need to think about it. Okay. What's the meaning of this? Eventually, this notion of a non-commutative probability space denoted by A and phi is it's an abstraction. So in real life, we do hope to analyze objects we care about and not just abstractions. In my life, these are typically matrices representing graphs, or not necessarily, but these are usually distributions over matrices. And the phi is going to represent moments of those matrices in the sense of the trace and the eigenvalues. But in any case, this is an abstraction. And the question is, can I generate free elements? Free elements are something that we are able to analyze. Typically, when you just have arbitrary objects and each one has its own distribution, if you don't know the connections between them, they are hard to analyze together if you want to analyze their sum or their product or what. This notion tells you something pretty strong. If in the set that you're analyzing, you have some source of Haar unitaries, okay? So it can have a different meaning. We've seen Haar unitaries in the homework. We've seen Haar unitaries for the group algebra, but there are Haar unitaries also for matrices. And assuming that you know, let's say, how to generate them in a way that's free from one particular element, if you have a source of Haar unitaries that you can generate, then you can sort of generate an infinite amount of elements that are free from each other. So it's enough for me to have one element, one matrix, one graph that I can construct, and then I only need a source for free Haar unitaries, and I can create an infinite amount of other elements with the same properties as my original one, just that they're free from it. So this may look a little vague right now, but this is pretty much the way we are able to analyze random graphs using these techniques. We construct one good graph, and then we summon Haar unitaries somehow in a way that's we're able to generate as matrices, and then we have a supply of graphs which are analyzable together. Okay, I hope this made some sense to some of you, and if not, it will be anyway clearer as we go on. Okay, so more questions about this before we move to the Cauchy transform? All right. So next we talk about the Cauchy transform. Recall will be denoted by this fancy mu. So I have a probability measure mu, and the Cauchy transform variable x is defined as the integral over the reals of 1 over z minus t in mu of t. And we also prove that in the proper region, defining this equals the sum from n goes from 0 to infinity of the nth moment of mu divided by t to the n plus 1. Keep forgetting the plus 1 here, but then and we've seen that we can move back and forth between a distribution and in the Cauchy transform. Okay, the direction to the right is just this calculation, and to the left it's the Stieltjes inversion formula. And I want to show an example of using it, using something that we've seen in the first week of the course, which is the distribution of the following element. So we look at the U, which is a Haar unitary, and we analyze we care about the element A, which is U plus U star. Okay, this is self-adjoint, so I can ask what is the star probability, what is star probability distribution in the analytical sense. So recall that for asking about the analytical sense, we start with the algebraic sense, and we want to know what are all the moments. What are the kth moment is the moment phi of a to the k. So this equals phi of u plus u star to the k. And we analyzed it. I don't know if you remember what it was. It wasn't Catalan.
Yeah.
Okay, arcsine was the probability distribution. We'll get there soon. But what were the moments, first of all? So the arcsine is the distribution of A in the analytic sense. But in the algebraic sense, the distribution just means the infinite sequence of moments. So it's, yeah, K choose K half, or even K. Even K, and it was 0 for all. Okay. We did it in the first week. And back then we said, okay, how can we work with this thing to get the distribution in the analyticals? It's a probability distribution mu. And we just said, okay, leave it for a second. We don't know what's the recording of the first week. I said, okay, this looks interesting, but I don't know how to handle this, like I knew other stuff. But we use the fact that we know the star distribution of a Haar unitary, recall was just the uniform distribution over the unit circle, to plug it in to a calculation using the moments of A, to get that this is going to be the arcsine distribution. But we had these moments and we didn't know what to do. Now we have an additional trick that we can apply to get the distribution in the analytical sense, and this is the Cauchy transform. So if I have, assume that, so now I have the moments, I can plug them here and try to get some useful representation of the Cauchy transform. And if I'm able to do so, then I'm able to invert it to get mu. Okay. So how do we get the Cauchy transform of representing these moments?
Find the cancellation of the binomial central binomial coefficients, right? Like we did in class.
Yes. So that's one possible. I actually tried doing that and I failed. That was a good approach. So to tell the truth, even beginning, I'm not sure next week, but probably the week after, we'll be able to get the Cauchy transform from other sources. Currently, we don't have, but we are able to use combinatorics to get it. And the way we're going to do it, and here I'm going to be slightly informal, is that if I think about the function, which is just the generating function of these numbers. So instead of I'm going to write an infinite sum here. So this would be from from 0 to infinity of these numbers.
Would be 2k over k.
Yeah, 2k over k. So this would be just a generating function of these numbers. If I am able to calculate this function, I am done with calculating the Cauchy transform because the connection that will hold is, if I have it right, pretty sure it's going to be 1 over z times c of 1 over z or something of that sort. Right? Okay. And this one is a generating function the way we are used to it from combinatorics. Okay, so if I'm able to express this thing in a nicer way, then I'm done. So I'll first start with a claim. And I'll prove it in the end. But the proof of it is going to be less important because the main thing I want to show an example of is how do we use the treatment form to get the distribution. And the claim is that the formula for C of x is right 1 over 1 minus 4x squared. And I want to mention two things. First of all, I wrote here both, I wrote the definition of G. So this is the direction of how do we go from mu to G of mu. I didn't write the other direction, which is the Stieltjes inversion formula. So I'll write it down soon. I want to mention one other thing is that this is pretty similar to something that we might or might not see later in the course, which is something that's called the moment transform, which some of you may encounter in the towards the end. And the moment transform of a probability distribution mu is pretty much defined as the same as this one, just ignoring the trivial moment, the zero moment. Okay, the zero moment of every distribution is 1. And this is called the moment transform of the probability distribution. But anyway, what we'll do now is from this get the Cauchy transform and then use it to get mu. So let's see how this is done. And now I'm going to just brute force use all the tricks we've seen in class without giving all the excuses from measure theory and Lebesgue integrals and so on. So now I apply the equation there. So I have that G mu of z. Do it without making a mistake. So this is 1 over 1 minus square root of 1 minus 4 over 3 squared. Right? And I push z inside and I get 1 over z minus 4 squared minus 4. And now I want to calculate what's mu of the interval AB, and I'm not saying what's the range for A and B just yet. And from this is going to be the Stieltjes inversion formula. this is minus 1 over pi. Let's write it one time properly. Limit epsilon goes to 0 of the integral between a and b of this thing, where for z I write x plus I epsilon. So this is 1 over plus I epsilon squared minus 4 root dx. Imaginary part. And now what I'm going to do, making no excuses, because you heard all the justifications for it today, is going to be 1 over minus 1 over pi, the integral from a to b of the imaginary part of 1 over okay. I just put 0 for epsilon and that's it. Now, in this instance, in what's going to be the imaginary part of this thing when x is real, just when I need the term inside this to be negative, right?
We integrate only along the real axis.
Yes, always. Yeah, in the Stieltjes inversion formula, you integrate from a to b on the real axis, and you take the imaginary. Yes, so the support is going to be only in minus 22, and this is going to equal, well, let's see. So I need we have 1 over here. So if I write down 4 minus x squared square root, I take this would be the imaginary part. I mean, okay. Taking the imaginary part would just give me a minus sign because I have the I in the denominator. So I can write down this is the integral between a and b of this one. Which tells me that I can call this thing u of x. Okay, and this is and if for every interval the probability distribution is defined by how it's behave, like what's the probability mass on every open set. So for every a and b, I have this formula for the probability mass. So this is the probability distribution in the analytical sense for this. Now recall that this thing we've called it. The videos that the green isn't properly seen, so let's look at that. I call this of x, and we call this mu the arc sine distribution. Arc sine law, if you Google it, that's how it's called many occasions. And remember that we got directly to it on the first tutorial without treating first the moments, which I haven't said even how am I using here. We got it directly by the star distribution of the Haar. We'll need to recall that, but we first calculated what is the what's mu, what's the probability distribution in the analytical sense for the Haar unitary, plugged it in here, and somehow changed variables and got to this distribution. Okay, and this time we went through the moments. However, the way I'm using the moments to get to this formula is going to be tricky. I'm not going to be totally about it, and it's not really a part of the time of a course that will be taught next semester. So let's do it. So if you feel like you're losing me in this section, then it's okay. But this part is really important to know how to deduce the probability distribution from the Cauchy. Okay, so how do we prove the claim? The idea is to look at these numbers, k choose k over 2, and think what is the object that we're counting here, and how else can we describe it? And when I see k choose k over 2, I can think about many things. I think about walks on the integers. So let's say I have the integers, and I have a sequence that starts from 0, so on, and I have -1 and -2, and so on. And I want to have a walk that starts from 0 and goes back to 0 on this axis. Okay, so if I have k steps and I want to return to the origin, I need half of them to go right, half of them to go left. So the number of walks that will return to the origin would be k choose k over 2. Oh. So, and now I'm using, as we did, I don't remember if it was the previous class or the one before that. I want to write immediately the generating function for this. And I'll call this class of cycles ending at 0, so not like closed walks ending at 0. I'll call them fancy C. And I want to say that C can be written, look at my notes. And first I want to define two other elements, two other sets, A and B. And these are walks that close at 0 only once. And they start with a step round. Okay. Starting like this. And B would be the other one when the first step is negative. And so the class of all the possible those blocks can be written as a sequence of a disjoint union of walks type A of start each time you close a cycle, you either start with a positive step or with a negative step, not both. And using tricks from generating function theory, without mentioning this is actually called the symbolic method. It can be shown that the generating function for the number of such cycles any size can be written as 1 over 1 minus the generating functions for the disjoint union of A and B. But notice that by symmetry, these have the same counts. There's no preference in either doing the positive one or the negative one. So I'll just write down 2 times the generating function of A. And we want to know what's the generating function of A. And
like that. like paths can go here you
For A.
yeah.
Yeah, and A is just the generating function can be written as so. I need to start with one step, then do a sequence of A steps, and then go back one step left. So this can be written as so the first step is counted by the element Z, then I have a sequence. Oh, now with A, I treat A only as other A's, right? Because I don't, I can't allow going back because then I close the cycle. I want to control when it's closing, and the other Z is for the dust. And once I solve all this, I get to the functional equation. Let's see how it looks like. So here I solve for A, and then I can plug it in for C. For C, just a moment.
You get what you want. You should get what you want.
Yes, I should get this, but I want to get first the functional equation. And oh no, I first solve. Okay, this is the functional equation for A. I solve it for A. I plug it in here, and what I get is what I. But this is like אני מסיפור אחר. This is a
Promotion for my course.
yes, it's a different field. The idea here was can I get directly a Cauchy transform without with just the knowledge of the moments. Sometimes I can use the moments to I understand them combinatorially, so I can write a generating function, and from that point on, it's just your calculation. So in any case, this is not part of our material. The most important part is that given that I have the Cauchy transform, I can calculate the probability distribution in the analytical sense, something that we needed some other kind of information to get here in the first questions, either about the Cauchy transform or about the freeness. All right. See you next week.